7:30. Oh, let's have to start. Just as a reminder, if you do not have the group that you have signed up with on the sheet by lecture Friday morning, I will assign you a random group. And for those of you that do have groups, you can fill out the preference for which paper you want. You can pick your top 3. So we're continuing on this chapter with single cycle in mind. So we're still looking at this more simplified version of the MIPS implementation. And this is our data path, but now we've added this control block. And what's input into the control block?
Good.
Opcode, right? Because opcode will tell us what the format is and what the format. That's all of these different signals. Am I using RT as my destination register, or is it going to be just a read register? Or is my destination register RT? The only other type of instruction that I need more information from other than the opcode is my R-type instruction has this funct code. And that funct code gets input into the block along with ALU up, and that tells the ALU what's. So these are the 2 blocks that we're going to focus on creating today. Now we're going to start with the ALU control block. And remember, this was our full ALU, well, what we started with, right? And the opcode was telling us which of these inputs into this final mux we needed to select, which was giving us the results that we wanted. And this is just what we did before, right? What were these control signals? This is not the exact ALU that we're going to use. It's just to remind us that what is this operation code that we're trying to generate? Okay. So the ALU is going to be used for load and store. And when it is doing load and store, what it needs to do is add, right? So I need to add the base address and the sign extended immediate together. For a branch, I need to subtract, right? Because we're going to subtract and see if these 2 things are equal by setting the 0 flag or not setting the 0 flag. And then for R types, it depends on the funct field, right? And here is a table of the ALU control code. What is the function? What is the instruction? Right? So if I get 0, 0, 0, I'm going to do an AND, which corresponds to my AND instruction. 0, 0, 1 is OR for my OR instruction. So this ALU control, it gets the input based on opcode and the funct code from the instruction. So we can create this table, the truth table, right? But one thing that we can do before we create the truth table is we can simplify the opcode. Because we do not need to know all of the opcodes. The only time that we need to make a specific change to the function that the ALU is going to do is if my opcode is R-type. Otherwise, the opcode tells me everything I need to know. So I can simplify it to these 3 different combinations. If I'm load word, store word, my other control block, the main control block, is going to give me the ALU opcode of 0, 0. And now if this ALU control gets 0, 0 on the ALU op. I know that the format is load word, store word. I can ignore funct code. I just need to tell the ALU control I need to add, right? And if I get the opcode 0, 1, again, funct code doesn't matter, right? There is no funct code if I'm a branch. This block just needs to tell ALU control, subtract. But if we get the code 1, 0, that's when the ALU control is told, okay, now look at funct code, right? And then based on the funct code, we can do and, or, add, subtract, all these things. So here is our truth table. And like we mentioned, if we get 0, 0 or 0, 1, that means funct code does not matter. It's all don't care. But in terms of our ALU control, I need to add, subtract. So I'm adding for load word, store word, subtracting for branching. But if I get R type, which is 1, 0, then I need to look at funct code. Okay. And these are the different funct codes or the different operations. And based on the operation that we need, that's what the ALU control output would be. So now I have this table based on inputs, right? ALU up and funct. And I have my outputs or ALU control, right? So this is basically just a truth table. We can create K-maps, one for each output, and we would be able to draw the digital logic circuits for this implementation. And here is the truth table, a more simplified form without the descriptions, right? So I have these 1, 2, 3, 4, 5, 6, 7, 8 inputs and 1, 2, 3, 4 outputs, right? So these K-maps would be rather large. I'm not going to ask you to make these K-maps. Just know that's how it would be done, right? And you wouldn't do the K-maps by hand. You would input this into some program that would tell you what the digital is. If you wanted the optimized two-level logic. And if you did some optimization and you use that truth table, this is our circuit that we've come up with. Most of the time, we can figure out everything from just ALU up, right? So we have ALU up, and we have funct. And this simple digital logic circuit gives us our 0, 1, and 2, so 3 outputs. And it's different from 4 because here all of the most significant bits all 0, right? So this is our control block for that first thing in the bottom right-hand corner for ALU control. We need to do a very similar thing for the larger control block that takes in opcode. Okay, so this one down here. We still need to handle this one, right? And this one is going to control like all of our muxes, right? Regdes is a mux. Branch is an AND gate for controlling the mux. It takes in the 0 flag and the branch, right? And then mem read is for memory. Mem to reg is another mux. ALU up we just talked about to simplify it to 2 bits. so that we can have simpler control down here. Memwrite is for memory. ALU source is a mux. Read-write is for enabling writing systems. So these are all of our control lines. Regdest was a mux and it's to control the source of the destination register. So this is either RT or RD, right? Read-write enables writing a register in the register file. So if this is 1, whatever is on the inputs to the data line of the register will be written to whatever's on the inputs of the destination register. ALU source is the source of the second ALU operand, and this is either RT or the sign extended immediate from the instruction. PC source, this is either PC +4 or the branch target address. Memread memwrite for reading and writing to memory, similar to read-write. And then mem to reg is the source of the write register contents to the register file. So our main control units, the control signals are derived from the instruction. And specifically, we're going to derive it from the opcode, right, the first 6 bits. And our main control unit is not going to handle point code because the secondary control units down here, ALU control, handles that. So there are a few things that are simplified, right? RS is always read for R types and I types. It's not in there for J types, but our data path that we currently have does not support J type. And then RT is read except for a load word because it's destination. And then for our writing to the register file, it's either going to be RD or RT. And we always have this address or by type. So in order to implement this control block, we need to build out that truth table, right? Based on the inputs of opcode, what do my outputs need to be? So this is our first question. If we are going to set control signals for an R-type instruction with add, what do some of these control signals need to be? And your code is 639. Okay, so I don't see any new answers coming in. And we're not quite at the threshold, so do talk to the people around you. Read in front of these, explain how you got to the answer you got to for. Submit your answer to your type of check.
What did we get? So I was from the right to left. ALU code for the previous sessions. For if you're doing add, it's R type. The R type is 1 0. So I know it's C, D, or E. And then two regs, that one controls the final mux, whether or anything in the numbers. Our type you don't do memory, but we still need that mux to allow the result from the ALU. So it's like the 0, that's the ALU result of that point is 0 1. So from there, we have to go to register destination. And that's the one that's that first box to the left of the registers, and that was control whether we have RDs. And since it's an R type, we have our SRT that needs to be 1 to allow the instruction 15 to 11, which is the RD instruction going. And so I got D from that one. I had to look at the slides to remember what the ALU opcode was. Personally.
You would want to set your because you're just using registers. Registers, you're not doing longer. And you want destination registers. I did first. I think I did right. Numbers are registered. I'll put with the ALU. So that's 0.
Okay, so discussion has died down and we did have some code movements in the poll. Let's just do these one signal at a time, right? So register destination. I am an add T1, T2, T3. I have RD. So my destination register needs to be RD. So that means that this mux, in order to select RD, the inputs for the control needs to be 1. So we like B or D so far. We haven't ruled out E though, right? Mem to reg. That is this guy over here. And again, we're R type. So we're not reading from memory. Our result that's going to be written back is coming from the ALU. So this control signal needs to be 0. Yep. So again, like B, D, or E so far. And I'm R type. So my ALU opcode, this thing right here, we covered at the beginning. 1 0. So it should be D. 1 0 1 0. 0 0 is for store word level. So we can fill out the rest of these fields for R types because for all of these R types, these control signals are going to be the same. So let's see. Register destination, we talked about, it needs to be 1. ALU source, we didn't talk about. What does it need to be? That's this guy right here. It needs to be 0. Because we need RT. Source is 0. And to reg, we talked about that one, is 0. And then reg write. Am I writing to the register file if I'm R type instruction? Yeah. Otherwise, my result is not stored and I did nothing. Do I read from memory? Does it matter if I read from memory? Yeah, it doesn't matter, right? Because mem to reg is going to be 0. So whatever comes out of memory here, it's not going to be selected, it's not going to affect the data path. So rather than writing a 0, I can put an X here, and maybe I can make a more efficient control logic with this flexibility. What about mem write? Am I writing to memory? Does it matter if I write? Yes or no? It's not just because of that. We do have an address. It is going to be calculated coming out of the ALU. Is it a meaningful address? It could be, but it could give you bugs in your program, right? Because you'll be writing to memory. You didn't mean to. So this needs to be 0. We can't be flexible with that one. Because the result of our add would be used as the address. And then whatever was RT would be written to that address. And we don't want that to happen. Branch. Is it a branch instruction or not? Does it matter if I make this 0 or 1?
Shouldn't, because the 0 flag would stay 0, wouldn't it?
What if my add result turns out to be 0? Like say if my register content for RS is -2, my register content for my RT is also -2, and I'm doing subtract as R type, then the 0 flag would be 1, right? So this is also important that we keep it 0, because this 0 flag would be generated. So to stop it from branching to some weird instruction space, that's why the branch control signal exists. Otherwise, it just wouldn't exist, right? And then ALU op 1, ALU op 0, we talked about. This is 1, 0. You don't have to memorize this. If you just say it needs to be an R type, you can do that. Or you can say that it should know to add based on whatever the R type instruction is. That's fine too. But all of these other ones, you should know. So for a load word, register destination, what does it need to be? 0, because I need my destination register to be RT, right? ALU source. And over here. We need the sign extended immediate. So it should be 1. Mem to reg. Be 1. Because I am reading from memory, and I need that result to be written to the register file. So it's reg write, also 1. Mem read. If it's not 1, I'm not getting any data out of the memory. Mem write. Right, it needs to be 0, because again, if it's 1, I'm going to write some random data from RT to that memory address. Branch. And then ALU op 0, 0. And store word. Register destination. Is there a register destination for store word?
Is it stays in the data memory, right?
We're not writing anything in register file, right? Does it matter if this is 0 or 1 then? Gives me more flexibility to make a more efficient circuit. Okay. ALU source.
One.
Needs to be 1. I need that sign extended immediate. Mem to reg. Does the store word in this be 1? I'm not reading from memory, right? I'm just writing to memory. But is it important that this needs to be 0 or 1? Yeah. So again, I can be flexible. Reg write. Absolutely needs to be 0. I do not want to write random data to the register file. And it is mainly that because this signal is 0, that's destination doesn't matter and mem to reg doesn't matter, right? Mem read. Am I reading from memory?
0.
Does it need to be 0? Yeah. We don't care if we read. Because that data is not being written anyway. Mem write. Branch. ALU off. Right. So a branch instruction. Register destination. Matter? Source. We need this to be 0 because we're using the ALU to subtract the 2 register operand. M to reg. Like the store, it doesn't matter, right? Because this is right. Does it matter if we read from memory? Yeah. What about writing? Yeah. We better not write to memory. Branch needs to be 1. And our ALU off is 0. Okay. So these are the different control signals that you should know. And it's important that you know when it doesn't matter if it's 0 or 1. Because if you know that it doesn't matter that it's 0 or 1, when you draw those K-maps, you'll have those X's, and the X's you can force to be 0 or 1. So maybe you can draw those bigger essential prime increments and get a more efficient circuit. So here is a different table, but this table does not have the X's for everything that it can have the X's. Use these ones. Right. So the truth table for control functions. Okay. So we have our inputs, which is opcode, and we have all of these outputs that we just talked about. And then for our formats, opcode is 0, and the output's all the same. For load word, this is our opcode. These are our control signals, store word. This is our inputs. These are our control signals. and branch logic flow. This is opcode. These are outputs. And again, we can make this KMAC from the truth table, implement it, and we would get something like this. So this is our two-level logic, right? We have and then or. So this is the digital logic circuits that would go into that big logic block. And we would need, if we wanted to add support for more instructions, like jump or and immediates or immediates, we'd have to go back to the truth table, add the outputs that we need, and then re-implement this digital logic circuits. So, like I mentioned, adding in new instructions. This potentially requires modifying the data path. And also potentially requires adding more control wires or signals, which would impact our previous truth table. So if we impact the truth table, we have to re-implement control. So if we wanted to implement jumping, right? This is not in our data path yet. And jump is using opcode is 2, and then the address needs to be assigned to the bottom 26 bits of PC. And the top 4 bits of the old PC are the top 4 bits that we use. So we need an extra control signal to be decoded from opcode in order to do this. Because currently the only thing that we can set PC to is PC plus 4 or the branch target address, right? So we've added this additional mux here. After the mux that is choosing between PC plus 4 or the branch target address. And here is our other inputs. So one of the bottom inputs is from the first mux, right? So was it just PC plus 4 or was it the branch target address? And the top inputs is going to be our jump target address. So to get our jump target address, we take the instruction, bottom 26 bits, shift it left by 2, right? Because our bottom 2 bits are always 0. And then append the top 4 bits of PC plus 4 to get the 32-bit jump address, right? And that is, if we have jump as 1, we would select this jump address. So our new control signal is this jump signal. So we've modified the data path, added a mux, and because we added a mux, we need to add a new control signal. Since we added this new control signal, we need to re-implement the logic for this control. We didn't touch the control down here, right? So we don't need to re-implement this one. So then the next question is, we don't have support for add immediates or immediates and immediates, right? We didn't talk about that yet. What do we need to do in order to do this? Do we need to modify the data path? What do we need to modify? So that's modifying control. Do we need to modify the data path? We don't need to modify the data path. Everything that we need is here, right? We can read from RS, we can read from RT, right? And we can select. Well, we can write to RT is what I should say, right? And then we can select the sign extended immediate for the ALU. So there's no problem there. But the main problem is we do have to change our control. Because we need to be able to make sure that the destination register is RT. And that this ALU source over here is the sign extended immediates. And we're not going to write to memory. And this and to reg is going to be taken from the ALU. And because we changed all of those, we're going to re-implement control. Okay. And then what about jump register? Do we need to modify the data path? What does jump register do though?
It's gonna go to the address stored at the, was it 31st register, was it?
Well, that's jump in link.
Oh, that's jumping lane.
But jump registry,
Oh, just the registry you specified.
so jump registers.
You would have to check for a data path for somewhere for the register to reach the PC.
Right now, there's no way for the register to reach PC, right? So we would need to be able to get from these read ports, one of them. Add another mux over here, add another control signal that I'm a jump register. So how we created this data path, we looked at the instruction sets. What are the data path requirements, right? And we connected those data path components in their proper order. And we're going to establish a clocking methodology. Our clocking methodology that we covered so far is just single cycle. We will talk about different methodologies in the next lecture. And once we had the data path, and we analyzed the implementation of each instruction to determine what the controls need to be, then we could implement the control blocks with K-maps and assemble control logic. And if we wanted to add anything new, like how we were talking about extending our data path to support these different instructions, add I, jump register, and then also jump, right? We just have to ask ourselves, does our data path need anything new? If it needs to be changed, then we implement that change. And then we look at the control. Does the control need to change? If it does need to change, I need to go back to my truth table, add the control signals that I need, or modify the current ones that I have, and re-implement my visual logic equations. So one of the big problems with this single cycle data path is performance. So what is the shortest cycle time for this data path? And it's saying that we have these different stages, right? Memory, ALU, and adders are 100, and the register file is 50. And if we created a table based on our different instruction types that we have. Our ALU type or R type, all of our instructions are going to first get instruction memory, right? We need to fetch the instruction. Most of our instructions are going to read from the register file. And most of our instructions are then going to do this ALU operation on the registers. And some of them also need to access data memory, being load word or store word. But on top of all of that, my load word then needs to go back to the register file to write to it. So for my single cycle implementation, my frequency or my cycle time needs to accommodate my longest instruction. So my longest instruction, load word, right? So even though jump can be done in 200 picoseconds, in the single cycle implementation, jump will take 600 picoseconds. Every single instruction will take the same amount of time, and it's defined by the longest instruction. So this is pretty inefficient, right? But it is very simple to understand, right? The longest delay, which is determined by the critical path. Here we find that it is the load word instruction. Determines our clock period for all of our instructions. So next time you guys are reading about pipelining, we're going to talk about how we can improve performance with a slightly more complicated data path than pipelining. So that is your next chapter. And just a reminder, do sign up for those teams. If you have not created a team yet, I will turn the file to read only.
For the instruction for the presentation posted for us to take a look at.
Not yet. But it's just 12 minutes. Maximum. 10 minutes minimum. I'm going to give a tutorial on the topic that you do.
Right.
Oh, yeah. You're gonna have your references. I'm going to try and give you your topic reference, but it's not always possible.
Understandable.
For now, it'll start off.
What do you guys want to like?
Yeah, reading the paper.
Let's do it.
Yeah, that's fine. I see.
Yeah.
This is the. We basically just copy those tables now.
There's that much.
I